This video is about special right triangles, and it's found in your text in section 8-4. Why special? Why would we think a certain kind of triangle was special? Well, mathematicians call some triangles special because they're simple, beautiful, and they're found in everyday life. For example, 45-degree, 45-degree, 90-degree triangles are just half of a square. So we have a special theorem just for those kind of triangles. If we have a right triangle with two 45-degree angles, it looks like this. And the theorem says that in this kind of triangle, the hypotenuse, I'm going to call the hypotenuse C in this case, and remember that we can identify the hypotenuse by finding the side of the triangle that's directly across from the right angle. The hypotenuse measures the square root of 2 times the measure of a leg. So let's call this leg A. What this theorem is telling us is that C, the measure of the hypotenuse, equals the square root of 2 times A, the measure of a leg. It happens to be the measure of either one of the legs in this triangle because being an isosceles triangle, it has these two sides congruent. So let's do an example with this theorem. We can find missing sides pretty easily now, now that we know the ratio of certain sides in this special right triangle. We're told that A is 4. First, we're asked to find B. Well, we've just talked about the fact that this kind of right triangle is isosceles because if one angle is 45 degrees, then the other base angle must also be 45 degrees, since when we subtract 45 from 90, we're left with 45. So 45, 45, 90 triangles are isosceles. A is 4, therefore B is also 4. We're asked to find C. Now by our theorem, we're told that C is the square root of 2 times A. So here we have the square root of 2 times the measure of A, which is 4. And we usually write it in the reverse order, 4 times the square root of 2. That's just a mathematical convention so that we don't accidentally think the 4 is inside of the radical sign. Okay, here we have another example, and this time we're given the measure of the hypotenuse. So we have that C is the square root of 14. This is the same kind of special triangle. We have these two legs being congruent to each other, and we have the theorem that says C equals A times the square root of 2, or the square root of 2 times A. We can write it either way. So let's substitute in a value for C. We have C is the square root of 14. That must equal A times the square root of 2. Now we can divide both sides of the equation by the square root of 2. On this side, they cancel. And on this side, remember from the simplest radical form video that we went over the rule that says if you have a square root in the numerator and another square root in the denominator, you can put both numbers under one big square root sign and have the whole fraction inside of the radical. So we're going to do that. We're going to put 14 over 2 inside of the radical. And now, running out of room here, we have the square root of 14 over 2 is the same as the square root of 7. And that cannot be simplified any further because 7 is a prime number. So we've just found that A is the square root of 7. And since A is the square root of 7, B must also be the square root of 7 because a 45, 45, 90 triangle is isosceles. You try this one, filling the missing value in this table. Okay, here's our other kind of special triangle. And we can see it in what this person has done very creatively with this dollar bill. They have folded it so that we have an equilateral triangle made by the dollar bill. See if you can do this. An equilateral triangle on this side, and then there's a line coming down perpendicular right here that makes this special right triangle. It's a 30-degree, 60-degree, 90-degree triangle, and it happens to be half of an equilateral triangle. So in a 30, 60, 90 triangle, we have another theorem that's similar to the first theorem. We have that the hypotenuse measures 2 times the measure of the shorter leg. So let's call this leg B. So we have that C equals 2 times B. The longer leg measures the square root of 3 times the measure of the shorter leg. This is the longer leg, and so it measures the square root of 3 times the measure of the shorter leg, which again, square root of 3 times B. So I've labeled these sides in relation to the shorter leg of the triangle. Just to review, the hypotenuse is the side directly across from the right angle, and the two other sides of the triangle are called legs. Okay, let's do this example. We're asked to find the missing values in this table, and we have a right triangle that is a 30, 60, 90 right triangle. How do we know that this angle is 30 degrees? Well, we can just add up 90 and 60, and in order to reach 180 degrees, what's left over here is 30 degrees. So let's use our new theorem to find out the measure of angle of sides D and F. We're given that side E is 5 times the square root of 3. Okay, so our theorem tells us that the longer leg, E, measures the square root of 3 times the measure of the shorter leg, D. And we're also told that the measure of leg E is 5 times the square root of 3, so I'm substituting that in for E. On the other side, I'm leaving this the same, the square root of 3 times D. Look at this. I can divide both sides by the square root of 3 and end up with a very nice answer. D is just 5. So I have D equals 5. Now my theorem also tells me that the hypotenuse of the triangle, in this case F, measures 2 times the shorter leg's measure, 2 times 5. 2 times 5 is 10, so F was easy. We can write that F measures 10 units. You try this one. Fill in the missing values in this table. Okay, let's do another example with a 30, 60, 90 triangle. Again, we know that this angle is 30, that's 60, and that's 90. This time we're given the measure of the hypotenuse, F equals 10, and we're asked to find the measures of the two legs. So our theorem has told us that the hypotenuse measures 2 times the measure of the shorter leg. Since we have a value for the hypotenuse, the measure of the hypotenuse, we have 10, which is F, equals 2D. Dividing both sides by 2, we have D equals 5. That wasn't so bad. Now we come to E. E is the longer leg. So the second part of our theorem has told us that the measure of the longer leg is the square root of 3 times the measure of the shorter leg, which is D for this triangle. So E is what we're looking for. It's the square root of 3 times, we've already found the measure of D. We know that it's 5. And just as a matter of convention, we'll switch the order of these two and write that E is 5 times the square root of 3. Okay, you try one just like that.